Picture a flat piece of aluminum. Now zoom in, past the scratches, past the grains, all the way down to the atoms. Now someone flips a switch, and millions of volts per meter slam across the surface. Oxygen ions slam into the metal, steal electrons, and, in a few trillionths of a second, a perfectly ordered crystal of aluminum oxide begins to grow, atom by atom. That self-building atomic armor is anodizing, and it quietly protects your plane wings, your phone's frame, your bike, satellites, even experimental microchips. Today, we're going to travel the world of anodizing and every aspect of the science and tech that anodizing and its applications offer to the world. Aluminum instantly forms a natural oxide skin just a few nanometers thick when exposed to air. Anodizing is what happens when we supercharge that process. During anodizing, aluminum is connected as the anode, another metal as the cathode or counterelectrode, and a voltage is applied. At the atomic scale, aluminum atoms at the surface give up electrons and become aluminum ions, Al3+. Meanwhile, water in the electrolyte splits. Oxygen species drift into the metal, aluminum ions drift outward. Under the huge electric field, they meet to form Al2O3, a dense, glass-hard oxide that literally grows out of the metal itself, not on top of it. First, a thin barrier layer forms, a compact dielectric only tens of nanometers thick. As voltage and time increase, acid at the surface starts to dissolve the oxide, while the field keeps pushing new oxide from below. The fight between build and dissolve spontaneously organizes into millions of vertical nanopores. Under the right conditions, those pores self-arrange into a near-perfect honeycomb. You've just turned boring metal into a precision nano-engineered material using nothing more than electricity and acid. Anodizing really took off in the 1920s and 30s when aircraft builders needed a way to stop aluminum wings from corroding. Early chromic and sulfuric acid baths made a few micron-thick oxide, good enough to survive salty air. By the 1960s, engineers learned to tune the oxide, thicker and harder for industrial parts, thinner and colored for consumer products. Modern planes, spacecraft, window frames, camera bodies all rely on anodizing to make soft aluminum behave like a tough, corrosion-proof ceramic shell. For decorative sulfuric anodizing, a typical recipe is roomish temperature, 15 to 22 degrees Celsius, sulfuric acid around 150 to 200 grams per liter, current density about 1 to 1.5 amperes per decimeter square, and 20 to 40 minutes. That gives you 10 to 25 microns of oxide, with pores big enough to die, but still protective. For hard anodizing, used on pistons or bike parts, the bath runs colder, 0 to 5 degrees Celsius, often with more acid and higher current. You can grow 50 to 100 nanometers of dense oxide, hard enough to rival hardened steel. Then there's plasma electrolytic oxidation, sometimes called micro-arc oxidation. Now the voltage jumps to hundreds of volts. Tiny sparks dance over the surface, locally melting and re-solidifying the oxide into ultra-hard ceramic-rich layers. Industrial anodizing plants look like battery gigafactories for metal skins. Parts arrive oily and dirty. First, they're cleaned, etched, and desmutted to strip alloying residues. Then, robot arms dip racks of parts into long, steaming acid tanks the size of swimming pools. Huge rectifiers pump thousands of amps through the bath. Operators watch current time curves like cardiograms. Any blip means trouble. After anodizing, the pores are either dyed or left clear. Finally, parts are sealed in hot water or nickel acetate, hydrating the alumina so the pores swell shut like closing millions of microscopic umbrellas. Thickness is checked with eddy current probes or optical microscopes. Aerospace specs can be tight to within a micron. All of this happens continuously, 24/7, in factories coating millions of square meters of aluminum per year. Researchers now use anodic aluminum oxide as a template. Fill the pores with metal or polymer, dissolve away the alumina, and you get forests of nanowires or nanotubes for sensors, catalysts, and energy devices. AAO membranes are also being explored as ultra-precise filters for water, DNA, and even viruses. The pore size is so uniform, you can select what passes purely by diameter. This is no longer just lab art. Companies like Inradox sell AAO templates and membranes off the shelf, letting other startups build nanowire LEDs, photonic crystals, and biosensors without building their own anodizing lab. Using a technique called local anodic oxidation, researchers bring the sharp tip of an atomic force microscope just nanometers above a surface like silicon, graphene, or titanium. A tiny water bridge forms, voltage is applied, and a nanoscale patch of oxide grows right under the tip. Line by line, you can ink insulating oxide patterns only a few nanometers wide, effectively writing resistors, ternal barriers, or quantum dots directly into a device. Teams have used this to define nanotransistors in graphene, tailor memristor behavior, or confine electrons in single-electron devices. It's anodizing transformed into a nanoscale pen for electronics. If you want to design your own anodizing process, whether for aerospace parts, electronic components, or micro-electromechanical devices, the mental model is simple. Choose the metal and oxide you want and the active area you want to anodize. Pick the electrolyte that shapes how fast you build versus dissolve the oxide. Sulfuric, oxalic, phosphoric, organic electrolytes, or silicate-based for PEO. Then tune the field. Voltage, current density, pulse shapes to set thickness, pore size, and order. Then it's iteration. Vary time and temperature, measure thickness and hardness, test corrosion or wear, and feed the data back. Many modern lines can now use AI-assisted control, watching current and temperature in real time to keep every atom growing where it should. Anodizing started as a way to keep warplanes from rotting. Today, it's a bridge between heavy industry and nanotechnology. Every time you touch anodized metal from now on, remember, under your fingertips is a self-assembled forest of nanotunnels, grown by electricity, guiding atoms and electrons in ways we're only just learning to exploit. And that's the hidden world of anodizing, the atomic skin behind tomorrow's energy, electronics, and infrastructure revolution.